Hello! How are you? I'm beautiful, as always, but you knew that. Okay, let's learn about conservation of mass. I know mass is like the weight. And balancing equations. Conservation. No, conservationists are like Earth Club. They like to, look beautiful. No, they like to, keep things the way they are. Okay, observation. Mass never changes. Over the past several hundred years, scientists observed millions, wow, of chemical reactions. Scientists carefully measured and weighed the reactants, I wonder what that is, and products of these reactions, discovered that the mass of all the reactants always equals the mass of all the products, whatever those are. For example, if you react 4 grams of H2, okay, that's hydrogen, with 32 grams of O2, that's oxygen, you'll always make exactly 36 grams of H2O, that's water. The total mass of the reactants equals the total mass of the product, so 4 and 32. Okay, oh, and here's the equation. Okay, so this is the reactants on the left, and then the products, I guess, is what you're making, which are on the right. So we have 4 and 32 of this, and we get 36 of this. So they're equal to each other. Okie dokie smoky. So that's the observation. Now they're going to tell us the explanation. The number of atoms never changes. Hold on, what did they just say? They just said the mass never changes. Now they're saying the number of atoms never changes, and that's supposed to explain it. How can we explain why the total mass never changes? During a chemical reaction, atoms are rearranged. So rearranged, I know that means moved around. I think my handwriting's gotten worse, guys. They're not created or destroyed. In other words, the reactants will always contain the same number of atoms as the products. To make the number of atoms equal on both sides of the equation, coefficients must be added in front of certain substances. The coefficients represent how many quantities of each substance there are. For example, 2H2 means 2 molecules of H2. So this 2, then, is the coefficient. Because of this, coefficients must be distributed, multiplied, in order to find out the number of atoms present. So in 2H2O, there are 4 hydrogen atoms, 2 times 2, and 2 oxygen atoms. So we go 2 here, and then 2 here, and we imagine that's a 1. Okay, what's this showing? So this is the reaction 2H2 plus O2, but I'm noticing there are 2 H2s, because there's a 2 in front. And then 2H2O means there's 2 H2Os. And so we've got 4 hydrogen atoms, 1, 2, 3, 4, 1, 2, 3, 4. 2 oxygen atoms, 1, 2, 1, 2. Okay. Alright, what are these examples showing? This kind of looks like the same thing as this right here. You know, these drawings. It looks like these were blank, so I guess this is how to balance. How to balance. I noticed they're writing out all the chemical, like the elements, so HCl, well there's no subscripts, that's just HCl. MgOH2, that's 2 hydroxides, so they got OH because there's 2 hydroxides. And I noticed there's a line here separating these are the reactants, these are the products, I remember that. This is what's getting used up, this is what's getting created. And then HHO, MgClCl. So let's see, HH, oh, but there's 2 here too, so that's 4. 1, 2, 3, 4. Yeah, so no atoms created or destroyed. Cl's, yeah, there's 2 there. 1 there for Mg. 2 O's, 2 O's. Yeah, so everything's balanced, that makes sense. SiO2, there's 1 Si, 1 Si. 2 O's, 2 O's. 4 H's, 4 H's, 4 F's, 4 F's, and so yeah, it's the balance. Oh, look at the coefficient here. Oh yeah, so there's 2 of them. There's 4 of them. But there's 8 here, but there's 4 of the little chemical, of the circles, I guess, which is the chemical. Sexy. What a great way to start off our next semester. I think there's one on the page there that you can give a shot. Then you'll discuss it in class. See if you can do that one. Bye-bye.